Hi, in this video we're going to learn how to convert forestry data into estimates of forest carbon stocks. So we'll call this forest carbon plot math. Now, in a previous video, I discussed the basics of plot math, how to take forestry plot data and convert it into useful numbers. In this video, we're going to focus specifically on forest carbon. So a good place to start is to think about basic forestry data. And so basic forestry plot data, we're going to have a plot, and there'll be a bunch of trees in it. And this plot will have a certain size. So let's say that this plot is 1/10 of a hectare. Now, if we know how much carbon there is on 1/10 of a hectare, then we can extrapolate that to many hectares of a larger forest. And then we'll repeat this for multiple plots across the forest. And then we'll use that to generate the numbers. So the first question is, how much carbon is in a tree? So if we think about a tree, this tree has a certain amount of carbon in it. Now, carbon's an element, so the way that we would measure carbon is in units of mass. So what we need to know is, what's the mass of this tree? Okay, mass of tree. Now, we can't very simply weigh a tree. So there are basic equations that are called biomass equations. And the bio just indicates that it's the mass of a living thing. And these equations will take some measurable attribute of the tree and then convert it into a mass value. So the easiest part of a tree for us to measure, and one that's related to the amount of mass of a tree, is what we call stem diameter at breast height. Now, this is just a traditional place that we measure trees. We could take something like a tape measure or some calipers. We can hold them at about breast height and measure the tree. So it's a standardized place we measure the tree. And actually, breast height is standardized to be 4.5 feet above ground. So we're going to go up to the tree. We're going to measure it at 4.5 feet above the ground. And we're going to measure its diameter, its girth, how wide is it. And as you can imagine, the more massive a tree is, the more massive its trunk is. So there's a relationship between this stem diameter at breast height, which I'll abbreviate as D, and the mass of the tree. And this is a fairly known relationship and a simple relationship in some ways. And so basically, if we cut a whole bunch of trees down and weigh them, and then we plot their mass, and let's say mass weighed in kilograms, against the diameter in centimeters, then we'll get kind of a scatter of data that look like this. And what this means is, as the diameter of the tree increases, the mass of the tree increases exponentially. So this is an exponential function. And so we usually write this as mass equals I'm going to put C here, times the Greek letter alpha times D raised to some power. So this power here tells us how steep this curve is, right? If beta is higher, the curve is steeper. It's a steeper exponential rise. This alpha is a scaling factor, And this C is a conversion factor. And that converts mass to carbon mass. Okay, and so we could think of that, that's the fraction of mass that's carbon. So remember, carbon's an element that has a certain weight. So if we think of all the mass, all the matter in a tree, some fraction of that is carbon. So what we're going to do is we're going to use an equation like this one, and we're going to go and measure the diameter of breast height on the trees, and then we're going to use this equation to compute the mass, which is this part of the equation, and then the mass is multiplied by this conversion factor to turn that into carbon. So this part, this describes that function, and then this is the conversion factor. Okay, so understanding the basic conversion of tree measurements into tree carbon mass, we can think about what does the data look like. So we're going to visit these plots, okay? And in the data, we're going to have a plot. And then on that plot, we're going to have multiple trees. And then something that's very important is the species of the tree. So there's all kinds of different species of tree. So we have sugar maples, we have red oaks, we have Austrian pines. There are thousands and thousands of species of trees. Now, the species is important because the species affects this relationship. And one of the most important things is that the wood of some trees is denser than the wood of others. So if you think about density, right, is a mass per unit volume. So density is mass per unit volume. So a tree of the same species that has the same volume will have a different mass if its tissues are denser. And most of a tree is made up of wood. So we tend to think of this as being the density of the wood primarily, although leaves and other parts of the trees also have a density. Okay, and then we're also going to have the diameter, and then we're going to have the mass. So as we go to our first plot, we'll call that plot 1 and then tree 1. And let's say that tree 1 is a sugar maple, and it has a diameter of about 20 centimeters. And then we plug that into the equation, and we're going to get something like around 200 kilograms. Okay, so a tree that's 20 centimeters in diameter, maybe it'll weigh about 200 kilograms. Now, if we were to look at the next tree, we're going to go down. So we go to the next tree in our plot. That's tree number 2. Maybe this is a basswood. Okay, maybe this basswood has a diameter of 12 centimeters, and that's going to be about 60 kilograms. And then we're still on plot 1. Tree 3, it's a sugar maple. Let's say that sugar maple also has a diameter of 12 centimeters. Here's where the density comes into play. So a sugar maple is about somewhere around twice as dense as a basswood. So at the same diameter, this might be 120 kilograms instead of 60. Basically, we'll follow this all the way down until we've completed plot 1. And basically what we'll do is we'll sum the mass of all the trees on that plot, and then we'll get the mass of plot 1. And then we'll repeat the same step again on plot 2, and so on and so on. Now, remember, if we get the mass, then we also have to convert that into carbon. So the typical conversion factor is basically a half. And that's because studies have shown that if you take parts of a tree and you weigh them, and then you basically divide them up into all the pieces using mass spectrometry or some other methods, lab methods, that about 50% of that matter is carbon. So we typically use this as a rule of thumb. So basically, once you get your mass per plot, then you can convert that into carbon per plot by cutting that number in half. So just to give some realistic numbers, let's say plot 1 has a mass of about 3.4 metric tons, which equals about 3,400 kilograms. About half of that is carbon, so that's going to be 1.7 metric tons of carbon. So basically we've got these plots now, and we've measured trees on them, and based on the size of the trees, we've estimated how much mass is in them, and based on some known numbers, we've estimated how much carbon is in them. And so now we get a whole bunch of numbers from all the plots. So we're going to end up with a bunch of plot data, and we're going to come up with an average. And so that average is going to be the sum of the masses of all the plots divided by n is the average mass, and we'll call that the mass of carbon. So what we're going to get is the average carbon per plot. Okay? And a key in plot math, if you recall from the previous video, and I'll repeat it here, I gave you a simple formula that said value per plot, in this case times plots per hectare, will give me value per hectare. Okay, so the final step is to get this number, this average value per hectare, which for forest carbon stocks is going to be something like metric tons of carbon per hectare. And, just say that this was the average, then we would get an average of 1.7 metric tons per plot. And we had 1/10 of a hectare, so that's 10 plots per hectare. So basically what we found on 1/10 of a hectare, 10 times that is what we would find on a hectare. So it's going to be 17 metric tons of carbon per hectare. Now, in a lot of forest carbon accounting, this is the number that we would stop with. Now, if we wanted to know the total amount of carbon that was absorbed and is currently standing in that forest, which we call forest carbon stocks, that number would be this times the number of hectares. So if it was a 100 hectare forest and there were 17 metric tons of carbon per hectare, then that would result in 1,700 metric tons of carbon. So as I was saying, the forest carbon stocks that we estimated from the plots were 17 metric tons of carbon per hectare. So remember, a metric ton is 1,000 kilograms. Now, one of the reasons that we bother to calculate forest carbon, remember, is to understand the relationship between a forest and its exchange with the atmosphere. Right? So we're interested in carbon exchange between the forest and the atmosphere. So remember that in the atmosphere, carbon is a gas. Right? So the carbon in the atmosphere is CO2. Carbon that we measured here is basically tons of carbon. So in order for scientists to translate what this number means into a number that's meaningful for understanding exchange with atmospheric gases, we have a term that's called CO2e, or carbon dioxide equivalents. And this is an important number for international treaties, things like that, anything that is trying to relate forest carbon to issues like climate change. So, CO2e, why do we call it equivalence? Well, the carbon inside the tree, right? The tree is absorbing CO2 from the atmosphere. And then through photosynthesis, it's fixing that carbon into things like wood and sugars and other elements. So what we're saying is, what's the equivalent of gaseous carbon dioxide, which is the greenhouse gas, to what's inside the tree? So this requires a little bit of chemistry math. So basically, if we break down, okay, so if we want to think of CO2 equivalents, what does that really mean? We want to be able to relate carbon to carbon dioxide. And to think of that in terms of mass, we need to think of the mass of a carbon dioxide molecule. So we basically have some carbon in a gaseous form that's traveling with two oxygens, and carbon and oxygen, based on the periodic table of elements, have different weights. So carbon has an atomic weight of 12, and oxygen an atomic weight of 16. So that carbon by itself has an atomic weight of 12, but if we add the two oxygens, then we get 32 plus 12 equals 44. So this is an important number for us because that 44 is the weight of carbon dioxide, and we can look at that relative to the weight of carbon. So to compute CO2 equivalence, we're going to get the ratio of CO2 to carbon. And 44 over 12 is basically 3.66 repeating, so 3 2/3. So what does that mean? That means if I want to figure out the CO2 equivalence of this 17 metric tons of carbon per hectare, what does that equate to in terms of carbon dioxide that's been pulled out of the atmosphere? Then I have to multiply the carbon times the ratio of CO2 to carbon, and then I get the CO2 equivalence. Okay, so now that we know the formula, we can plug in the numbers we have right now. So if we have 17 metric tons of carbon per hectare, we're going to multiply that by our 44 over 12 CO2 over C, and that's going to give us about 62.2 metric tons CO2e. So there's a lot more carbon dioxide, if you will, trapped in the forest than there is carbon. And so this part of the carbon math is really important because it takes the numbers that we would use to describe the forest and turns them into numbers that are useful for another application.